All right, welcome to Physics 105, Chapter 4. Chapter 4 is about forces and Newton's laws of motion. So here are the objectives. We want to recognize what does and what does not constitute a force. We'll learn about some forces and how they act. These two are really, really important. We'll identify specific forces acting on an object, and we'll draw an accurate free body diagram of an object. I call this a force diagram. We'll be doing this Physics 105, Physics 106, force diagrams, incredibly important. They're easy, but they're incredibly important. Begin the process of understanding the connection between force and motion, F equals ma. Understand the relationship between forces between two different objects, Newton's third law. Okay, so first of all, let's talk about what does and what does not constitute a force. Okay, so if I hit that table, I exerted the force on the table. Agree? That makes sense. Now, pretend there's no air in this room. Okay. Okay, am I exerting a force on anything? No, because there's no air. All right, makes sense, right? So, this is not technical, but it's good enough. A force is an interaction between two or more objects. So when I hit the table, there's two objects, my hand and the table. When I was making a fool out of myself, I'm punching, but what am I punching? Nothing, so it's not a force. Okay, Sully. Okay, so, all right, so I'm going to pull Sully. Okay, now, so I exerted a force on Sully. Now, grab that, I'm just going to pull it. All right? All right, now, what was it that exerted a force on Sully? It was not me. It was the bungee cord. Thanks. So that's I'm not trying to be picky, but that's incredibly important because Sully was the object. The first time I was the object because I was directly pulling him. The second time it was the bungee cord that was pulling him. So the force was exerted by the bungee cord, not me. All right, here's a question and something that you'll want to know for sure. Okay, so a force is an interaction between two or more objects. Now, here's a force that we're going to talk about forever, weight. So the weight is the force of gravity on an object, and it's equal to the mass of the object times the acceleration of gravity. So honestly, we're going to use that so often. So memorize it. I mean, you don't even have to memorize it. You just will. Osmosis kind of thing, right? Okay, so it's the force of gravity on an object. So here, let's say this is me, right? So here's me, and this is the force of gravity acting on me. Weight equals mg. So this is the first object, right? Now, a force is an interaction between two or more objects. So here's the question. What is the second object? In other words, what is pulling on me with a force equal to my weight? Well, it's the Earth, right? It's the Earth. Because again, a force is an interaction between two or more objects, right? So the Earth is the second object. All right. A proton is placed at rest at some point A in a room that is otherwise lacking of matter. At some other point B within the same room, is there an electrical force? Now hold it. Don't get all scared because we haven't talked about electrical forces or anything like that. You don't need to know anything about electrical forces. You know enough to answer this question. So pause your video and think about it. This is a good question. All right, so we're back. So look, there's a proton. And that's all. So there's only one object. So if you only have one object, you can't have a force. So the answer is 2. Is there another force? No. a force requires at least 2 objects, and the room only contains the 1 proton. All right. What's the most important equation in all of classical physics? Newton's second law. So there's many ways to write it. Let's do it this way. So the acceleration of an object equals the sum of the external forces acting on that object divided by the mass of the object. Now that's not how you usually see it written. You usually write it A equals F over m. So here you have to be careful. Whenever we write F, we're lazy. What we really mean is the sum, or the total external force. That's what we mean when we write F. Okay, so A equals F over m. You don't usually see it like that either. So multiply both sides by m, and you get F equals ma. That's how we usually see it in a textbook, right? F equals ma. And of course, don't forget A is delta V over delta T. So that's probably the most important equation in all of classical physics. F equals ma. So F equals ma, which is m delta V over delta T. All right. So here's a question for you. Forces cause what? So pause your video and answer the question. Okay. F equals m delta V over delta T. That's a change, right? Change in velocity over the change in time. So forces cause changes in motion. That's the important thing. Changes in motion. That's why there's that delta, right? Change. So years ago, I read this letter to the editor in the local newspaper. I'd like you to read it. Let's just read it together. Bicyclists should be careful on sidewalks. Now, be careful. I want you to find, there's some errors in this letter. Linda Jackson's February 5th letter cites a difficult problem for bicycles and pedestrians. Unfortunately, there's not enough room for bicycles and pedestrians on the sidewalk, and not enough protection in the streets for two-wheelers. Okay, whatever. Here's what we want to concentrate on. Mass times velocity equals force. That means a bicycle traveling 3 or 4 times the speed of a pedestrian carries 3 or 4 times the kinetic energy as the other. A dangerous formula all around, one that calls for a change in lifestyle for some, and I don't think it is legally the responsibility of the walker. All right, what is wrong with that? Well, look, mass times velocity equals force. Totally wrong, right? Force is mass times acceleration. Okay, so that's one thing that's wrong. There's actually another thing that's wrong that we're not going to learn about for a while, but I'm going to show you anyway. So later on, we're going to learn kinetic energy equals 1/2 mass times velocity squared. Now this guy, who must have flunked high school physics, he says a bicycle traveling 3 or 4 times the speed of a pedestrian carries 3 or 4 times the kinetic energy. False! Because it's v squared. So if the bicycle travels, let's say 3 times the speed of the pedestrian, it's 3 squared, or 9 times the energy. Anyway, but again, just remember, mass times acceleration, or the change in velocity over the change in time, equals force. So don't write a letter to the editor if you don't know what you're talking about. All right. Here's Newton's first law. Newton's first law, an object at rest will remain at rest, or an object that is moving will continue to move in a straight line with constant speed if and only if the net external force acting on the object is 0. So look, here is a marking pen. It's at rest. It's going to remain at rest because the net force acting on that thing is 0. Now I take this thing and I throw it, and what happens? It doesn't go in a straight line. Why not? Well, because there's a gravitational force acting on it. On the other hand, if we were in deep outer space. Now, whenever I say this, deep outer space, I mean that we're far away from anything. And so basically there's no gravity. That's what I mean by deep outer space. Okay, we're far enough away from galaxies and planets and stars that we can just ignore gravity. If I were out in deep outer space, if I threw this thing, after it leaves my hand, there's no external forces on it, right? So it would just keep going at the same speed, the same direction, and it would never stop, right? And that's what Newton's first law tells us. Okay. All right, here's a good question, and I gave you a hint. The force needed to maintain a body at a constant speed in deep outer space is equal to what? So pause your video and think about this and then vote. Okay, we're back. Now notice it says to maintain in outer space. So that means that it's already moving, right? It's already moving. And so if it's already moving, what's the force needed to keep it moving? Nothing, right? Nothing. It's already moving. So that means it's already moving in deep outer space. The velocity is the same. So that means there is no change. So the force equals a 0. All right. Here's another question for you. Suppose you drop a bowling ball from a second-story window, and when the ball is about halfway to the ground, somehow the force of gravity suddenly ceases to exist. Describe the motion of the ball after gravity vanishes. Now hold it. Second-story window, so we're ignoring air resistance, okay? So we drop a ball from the second-story window. When it gets halfway down, gravity ceases by some magical way. What's going to happen to the motion of the ball? So think about it. Pause your video. All right, we're back. Whatever. Okay, so here's a second-story window, right? So we drop the ball. And of course, gravity makes it go faster and faster and faster. But then somewhere around here, gravity ceases. So what do Newton's laws tell you? Here, it's already moving, right? It's already moving when gravity ceases. So the external force is 0. So what's going to happen? It's just going to keep moving, right? Just going to keep moving with the same speed and the same direction, right? So same speed, same direction means the acceleration is 0. I mean, here, it's accelerating with the acceleration due to gravity, right? A sub y equals minus g. So here's accelerating because there's gravity. There's no gravity here, so it's not accelerating. So it stops accelerating and thereafter moves with a constant velocity, constant speed, constant direction. All right, not yet. Let's do an example. Another example. We did this. And I did something similar to this a while ago, but that's all right. Time in seconds, velocity meters per second. All right, so let's be lazy. A sub y equals minus g minus 10 meters per second squared. All right, we're not going to use 9.8, we'll just use 10. Okay, so let's say I drop something from rest. So initially it's at rest. So what is the speed, or the velocity? What's the velocity going to be 1 second later? Well, again, this means minus 10 meters per second per second. So what's the velocity going to be? Minus 10. All right. What's it going to be 2 seconds later? Minus 20. So you should be familiar with that from chapter either 1 or 2. I don't remember. Okay, now let's say I throw it. Okay, so I throw it. Where'd it go? Oh, there. Okay. I throw it at minus 40 meters per second. So, once it leaves my hand, the only force acting on it is gravity. So therefore, what's going to be the velocity 1 second later? Minus 50. 1 second later, minus 60. Okay, great. And again, we talked about that earlier, so that's nothing new. Okay, let's talk about something else. Let's talk about something called the normal or the perpendicular force. So here's a question for you. Okay, Newton's second law, F equals ma, or A equals F over m, whatever you like. Now, here I am. Earth is exerting a gravitational force on me, my weight. But I'm not accelerating. Now, according to Newton's second law, A equals F over m, if there's a downward force on me, I should be accelerating down. Well, I'm not. Well, why? Well, obviously, there has to be an upward force. So the net force on me has to be 0. So this upward force, what is exerting an upward force on me? The floor. So the floor is exerting an upward force on me that cancels gravity. Now, the name of that force has a whole bunch of names, actually. Most people call it the normal force. So, normal force. Now, normal doesn't mean like, the opposite of abnormal. It means perpendicular. So, perpendicular. So sometimes people call this the perpendicular force. So let's talk about it. So here's a picture of a table with a box. Now the box is, gravity is pulling down on the box, but the box is not accelerating, which means that there's an equal and opposite normal force. So the table exerts a force on the box, up. Well, what's the physical basis for that normal force? Well, okay, pretend you have a really good microscope, and now you're looking at the table. The table is made up of molecules, and the molecules are held together with molecular bonds. In physics, we model the bonds as springs. It's a good model, all right? So when the box, Earth is pulling down on the box, but these molecules are held together by these bonds, and so they're getting stretched, right? So the compressed molecular springs push upward on the object, okay? Upward, like a mattress or a box spring or something like that. So that's that upward normal force, okay? It's from these the molecules in the molecular bonds. Now, what happens if this box is so massive that it breaks these molecular bonds? Well, then the table breaks, right? Then the table breaks. Okay, so let me do a couple of crazy things. Okay, so just pretend that this box has a weight of 1 Newton. By the way, okay, so the weight equals mg. So the units, mass is kilograms, g is meters per second squared. So that's the unit, right? This is a force, right? Weight is a force. It's a force on an object due to Earth's gravitational pull. So the unit is kilograms times meters per second squared. But who came up with gravity and all that? Who really did a lot of work on gravity? Newton, right? Newton. So instead of saying kilograms times meters per second squared, the unit of force is an N, uppercase N for Newton. So, it's a way to honor him, right? Okay, so here is a block, and pretend it has a weight of 1 Newton. 1 Newton, okay? So, what is the normal force that the table exerts on the block? Well, the net force is 0, right? It's not accelerating. The weight is 1 Newton, so the normal force has to be 1 Newton, so that total external forces cancel. All right, now pretend that this is a 20 Newton box. All right, so now the Earth is pulling down on it with 20 newtons. So therefore, what's the normal force that the table exerts on the block or box? 20 newtons. So the net or the sum of the vertical forces is 0. Okay, now be careful. Well, okay, now let's say that okay, it's still touching the table, but I'm pulling on it, all right? Right, I'm pulling on it. So right now the normal force is 20 newtons. But if I start pulling up on it, what happens to that normal force? It gets smaller, right? It gets smaller. Okay, now look carefully. Now let's say, I'm so strong that I just lift it off the table. So now it's no longer touching the table. So what is the normal force that the table exerts on the block if they're not touching? It's 0, right? 0. Okay. All right, I have a bunch of questions now for you. An old, slow car moves at a steady 10 kilometers per hour down a straight highway, while another car zooms past at a steady 120 kilometers per hour. Which car has the greater net force on it? Now, I want to give you a hint. When you read a question like this, you want to really look at the adjectives. In fact, you probably want to circle them. I told you that before. So look at these adjectives. They will help you a lot. All right, so pause your video and answer the question. All right, so we're back. So what are the important words? Well, steady, straight. So the old slow car, the speed is steady, so it doesn't change. It's a straight highway, so the direction doesn't change. So for the old slow car, the velocity doesn't change. So the acceleration is 0. Okay? And how about this guy that's zooming past? I mean, they're trying to fake you right? They're trying to, to trick you, right? All right, now another car zooms past at a steady speed, and you're assuming it's a straight highway, right? So if this is a steady velocity, again, steady speed, and we're assuming straight, that means acceleration is 0. So for both cars, the acceleration is 0. If the acceleration is 0, what's the net force? 0. Okay? So see, that's the thing. People who write these questions, just like the people who write exam questions, they always put what's called distractors in the question. They're trying to distract you from what's important. So we notice here it says an old, slow car, right? So you're thinking this, old, junky car. Anyway, and this one zooms past, right? So you'd think, if you didn't know physics, you'd think, well, obviously, this guy has more force than that guy, right? It's zooming past. That's wrong. They're both traveling at a constant velocity, so the force is 0. Now, why is the force 0? Well, because there's air resistance and all other things. All right, but the important thing is same speed, same direction, same velocity, acceleration is 0, net force is 0. Okay, you push your 2 kilogram book along a tabletop, pushing it with a 10 Newton force, but there's also a 4 Newton frictional force. So what's the acceleration? So everybody stop your video and figure it out. Okay, we're back. All right, now remember, A equals F over M. And when we write F, we're just being lazy bums. It really means the total force. I guess we should put vectors, yeah? Okay, so the net or the total force. So here, we have 10 newtons that way, but then friction. Does friction help or hurt? It slows things down, right? So it's opposite. So it's 10 newtons that way minus 4 newtons, right? Because it's minus because it's opposite, and the mass is 2 kilograms. So 10 minus 4 is 6. 6 newtons over 2 kilograms is 3 meters per second squared. There you go. Okay. So it's important, right? The signs are crucial here, This is positive, that's negative. All right. The main point of Newton's law of motion is that forces cause what? What do forces cause? So pause your video and answer. Okay, what do forces cause? You better know this by now. Acceleration, F equals ma, right? F equals ma. Here we go, another one. Okay, an elevator is going up at a steady speed. So look at that word, steady. You underline that. If it were me, underline it. So an elevator is going up at steady speed. Identify the forces acting on the elevator. Well, think about it. I mean, we're going to be drawing pictures, so get used to it. So here's an elevator, right? The particle model. It's going up at a steady speed. What are the forces acting on it? Well, what are the forces acting on an elevator? There's weight, right? There's always weight, you know. If something has mass, there's always going to be weight equal to mg. But what's pulling it up? Well, probably tension, right? Tension. Okay, now, it's going up at steady speed. So the direction's not changing, the speed's not changing, so the velocity's not changing. So that means the acceleration, which equals the sum of the forces over m, acceleration is 0. So it has to be the sum of the forces, 0. So what are the forces? So the forces obviously are tension and weight, but if it's going at steady speed, how does the tension and the weight compare? Well, they're equal, right? They're equal. Okay. That's a good place to stop.